pleased to be able to present you a demonstration of the 2015 improvements in integrating your geological and geophysical interpretations within a robust and performant geomodeling environment. GeoGraphix 2015 brings an impressive list of significant enhancements to integrating geological and geophysical interpretations, including but not limited to our new velocity modeling in SeisVision that automatically ties your formation picks to their corresponding seismic horizons through a sophisticated 3D velocity model for accurate depth conversion. Improved integration between your geophysical and geological interpretations through the advanced velocity modeling, integrated seismic horizons and faults in the geomodel constraints, and dynamic depth-converted seismic backdrop in the smart section cross-sections. And then you'll view your geomodel dynamically in our improved advanced 3D visualization environment. We spent a lot of time in GeoGraphix 2015 to improve the speed, to reduce your cycle time from prospecting to production, through direct and seamless integration between the domains of geology, geophysics, petrophysics, GIS, and engineering. We've also striven to increase the accuracy of our reservoir interpretation through extensive 3D modeling, bringing all these domains together both in time and in the depth domains. All these should help your decision making to see all the possibilities in one 3D environment to make the best economic decisions possible. On to the demonstration. Today's workflow will be examining the Teapot Dome structure up in Wyoming. We'll model it in 3D with conformance technology of well data to examine and interpret the Teapot Dome structure in both geology and geophysical. We will then apply a new velocity modeling and depth conversion, which will then allow us to integrate the geophysical interpretation within the geomodel. And finally, we will visualize the interpretation in our new advanced 3D interpretation environment, and visualization environment. So let's shift over to the software. What you're seeing is the map view of Smart Section. Smart Section is our surface-based geomodeling application that has both a map view and a cross-section view to interact with the 3D model. Behind the scenes in Smart Section, I have running Frame Builder. Frame Builder is the 3D topology engine that can load surface information from either data points from well or data points from isomap layers, from isomap grids, and new to 2015, we can actually bring in depth-converted seismic surfaces and faults. It also has a constraints engine within the topology engine where I'm setting the Dakota as the controlling surface to the C1 dolomite. C1 dolomite is one of the reservoirs within the Tinsley, Pennsylvania system within the Teapot Dome. What you're looking at now is the C1 dolomite being modeled on the fly using triangulation and minimum curvature smoothing. I've got an east-west cross-section across the feature. Let's take a look at that. Where you can see that the shallower surfaces are being modeled more consistently because I've got more wells penetrating them. The deeper the structure goes, the fewer penetrations and the fewer samples, so the lower surface is being a little more naively modeled. Now if I apply the Conformance Tool, and I want you to see this all at once, so I'll try to get this all in one window. So I'll apply the Conformance Tool all at once. And you'll see that the Dakota surface here will conform the lower C1 dolomite surface. And you'll see in the map view that the C1 dolomite surface will then be extended outward to conform to the extent of the dolomite structure, of the Dakota structure. So next I will shift to my seismic domain. This east-west structure, or this east-west section I should say, is the same structural section as we were looking at over in Smart Section. I've used login to generate a synthetic seismogram to tie my geology to my geophysics. The B1 is this strong event up here. The Dakota is the strong event in the middle of the section, and the C1 dolomite is being modeled as the strong event down here. Now I'm going to go ahead and pick that C1 dolomite using our 2D auto picker, which has been vastly improved in this version of the software. So that's the east-west section. I'll also do it on north-south section. And return to the map view. I'm going to pick the C1 dolomite using the 3D correlation auto picker. Animated for your viewing pleasure. Now I've got three surfaces that are 3D auto picked. My shallow marker, my Dakota marker, and the one I just picked, the 3D, in 3D, the C1 dolomite within Tinsley. I've also done some post-act processing using LMKR volume attributes and then generated a time slice showing some of the compartmentalization within the teapot dome structure. These compartmentalizations are making some nice targets for some horizontal wells to be drilled in some of these old structures that have been producing for many, many years. Often if you cross a compartment, you may even find virgin pressures. Next, I'm going to create my velocity model using the three auto-picked surfaces of the shallow marker time horizon correlated with the B1 formation pick and well base, the Dakota time horizon correlated with the Dakota formation pick and well base, and that Tinsley time marker correlated with the formation pick in the C1 dolomite. By combining these together, I've created a 3D velocity model that I can then use to convert on the fly these surfaces to depth. Now when I apply the velocity model that I just built, notice that the time converted formation flags will immediately snap to their corresponding event, indicating that this is now a very full-featured, robust velocity model. Now returning back over into the Smart Section domain, I'm going to go back into my Geosurface Model Properties dialog box where I interact with the frame builder topology engine. And for the Dakota, instead of sourcing it from the data points from Wellbase, I'm going to source it directly from the Dakota depth converted surface coming from Seisvision. Likewise, I'm going to take each of the, I've got several faults in here. I've got an A fault that I'm going to source from the A fault from the 3D in the Seisvision interpretation. The B fault sourced from the B fault in the Seisvision interpretation. The C fault in the geomodel, again, sourced from the C. And finally, the main bounding fault to the west of the teapot dome structure will be modeled from the main bounding fault that we picked over the Seisvision 3D seismic environment. Go ahead and click OK. And let it go ahead and bring those surfaces in, put them in the constraints hierarchy within the topology engine, and go ahead and model through the entire structure. And now you'll see this is much more high frequency, much more detailed information because I'm taking the not only the well data, but I'm also going to be incorporating the seismic data. Now to incorporate the seismic data, I'm going to take my surface, actually let's take it from the Dakota from Seisvision. By taking it from the Dakota from Seisvision instead of the Dakota formation, it allows me now to combine both the Dakota and the Dakota from Seisvision together. So now when I model it again, it's going to be pulling the Dakota from Seisvision to control the Dakota, which includes the well pits, which will then constrain also the C1 dolomite. So in this way, I can also put in interwell points in the Dakota, which will be honored directly, but also be influenced by the Dakota from Seisvision. You can see I've picked up some information and some detail in this area. Now let's go ahead and look at our faults. I'm going to turn on my fault offset tool. This will generate fault intersections on the fly, and those fault intersections will then generate fault polygons dynamically. So go ahead and turn on that fault interpreter and let it go ahead and model through. takes just a few minutes, or a few moments. And see, I've now got fault intersections for the B fault in the C1 dolomite, the C fault on the C1 dolomite, and on the main for the C1 dolomite being indicated by these fault polygons. I'll just zoom in a little tighter so you can see the offsets a little better. And you can see the effect of the fault polygons being dynamically modeled, the bounding fault, the main fault, and these other minor ancillary faults. Now we can view all this thing together in our new 3D advanced visualization environment by selecting a probe. I drew a rectangle probe over the area, and I'm going to pull all the 3D objects, the wells, the surfaces, the faults, all into our new 3D environment. We can see all this thing modeled dynamically all at once. Now I've got the three surfaces turned on, the B1, the Dakota, and the C1 dolomite, but I'm going to turn them off because I want you to see my projected line of section, or my well-to-well line of section that I've got. Back in here I've got this line of section, and I've also got this line of section. These also were loaded into the 3D view as fits diagrams. And I've loaded in the gamma ray. So I'm going to zoom in here, and we've interpolated the gamma ray values between the wells so you can interpolate any kind of petrophysical attribute you want to within the line of section. I'm also able to select that fence diagram and display the seismic behind it, and then use the opacity control to blend back the petrophysical attributes against the geophysical attributes. Now currently I'm just showing the amplitude attributes, but if we had done some post-stack processing using LMKR's volume attributes, I could do an ESP, a curvature, and any number of other attributes that I could blend back and forth between the two to see what kind of influence that the seismic and the geophysical parameters have upon one another. Now, in addition, I can show the post-stack processing of the semblance that I showed you in SeisVision as a time slice, and let's view this from above. And let's change the palette. Semblances generally are better shown in the grayscale. Let's turn on that grayscale. And then we can walk down within the structure looking for any kind of compartmentalization that we may be able to see in the ESP, which could be a good place for then, now there's some compartmentalization showing up through here. Could be some indication of maybe some areas that may have more virgin pressures. So that's some good compartmentalization going on through here. Let's go and remove that and return to a different scene perspective. By the way, I'm using my Xbox game controller to control this whole scene. You can also use your keyboard. It's been optimized to use the keys very nicely. Let's go ahead and remove this surface, the seismic section. Turn back on my surfaces, and maybe let's go ahead and turn on the faults. And I can come back and activate, let's activate the C1 dolomite surface. By activating that surface, it should generate the surface contours for the C1 dolomite surface in the 3D view. In the future, we'll be able to do more interpretation here. Currently, we can pick the well tops within the log curves on the actual wells in here and move them to a different position, perhaps based upon some indication of seismic attributes or seismic structure to update that whole 3D model. So what have we done? We've looked at a conventional reservoir, the teapot dome, looked at it and geomodeled it with Frame Builder inside a Smart section to create a fairly robust 3D model. Then to get a further definition on there, we switched over to the seismic domain and picked the surfaces and modeled the Simon dolomite surface. We then created a 3-layer velocity model to convert from the time domain to the depth domain. Took those surfaces, inserted them into the 3D geomodel to then control the constraints and the shape of the surface away from the well control, and then viewed all of this in our new 3D interpretation environment. So let's wrap things up. I think you'll probably agree that GeoGraphix 2015 brings you improved geological and geophysical interpretations integrated within a 3D velocity model. LNPR enhances the GeoGraphix workflow experience by improved integration between the domains of geology, geophysics, petrophysics, and geomodeling. All this capability enables the creation of a robust and sophisticated Earth model to help target the optimum zone to lower your risk and improve your return on investment.